All right, let's dive right into this explainer. Today, we're building our mathematical toolkit to understand exactly how engineers control industrial machining. We're literally heading straight to the factory floor to decode the actual formulas that turn raw, chunky metal into hyper-precise components.
So, imagine you're standing right in front of a massive industrial lathe. You've got a super strict deadline, a heavy block of steel, and a single cutting tool. How on earth do engineers calculate exactly how long that part will take to make without pushing the machine so hard that the cutting tool literally shatters? Well, today, we're going to learn all about the physical levers that engineers pull to master this exact balance.
Here's our game plan for today. 1. Core parameters of turning. 2. Calculating time and passes. 3. The material removal rate. 4. Solving numerical problem 1. And finally, 5. Meeting the foreman's deadline.
All right, let's kick things off with Section 1, Core Parameters of Turning.
First up, we have feed. In formulas, you'll see this as a lowercase f. Feed is basically defined as the small relative movement of the cutting tool per cycle, usually measured in millimeters per revolution. Think of it like the tool's stride. Every single time the spindle spins exactly one full circle, how far does the tool step forward? Well, that's your feed.
Now, this builds directly into our next variable, feed rate, or FR. While feed is the stride per spin, feed rate is the actual linear travel rate in millimeters per minute. You can think of feed rate as the child of two factors. It's the spindle speed, which is n, multiplied by our feed, f.
And this right here illustrates a crucial distinction that honestly trips up a lot of folks. Feed, f, is a distance per revolution, but feed rate, fr, is a distance per minute. If you picture a runner, feed is the length of one single step, while feed rate is how many total meters they cover in 60 seconds. You absolutely need to know which one you're working with when you're setting up a machine.
Okay, our final core parameter is the depth of cut, or simply D. This one is super tactile. It's the perpendicular distance measured straight from the newly machined surface to the old unmachined surface of the workpiece. Put simply, it's exactly how deep the tool bites into the metal on a single pass.
Moving right along to Section 2, calculating time and passes.
Now, the absolute crucial point here is that you almost never carve away all the necessary metal in one single go. Doing that would just destroy your tool or totally stall the machine. Instead, engineers calculate the required number of passes based on the starting diameter, the final target diameter, and that safe depth of cut, D, we just talked about. You literally take the total reduction in radius required and divide it by your depth of cut to find out exactly how many trips the tool needs to make across the surface.
And of course, every single pass takes time. Machining time, or TM, is dictated by a really strict mathematical relationship. It basically links the total length of the cut to how fast the tool is moving, which, as we know now, is our feed rate. So a longer part, a slower spindle speed, or a smaller feed stride are all going to increase your total machining time. It's this giant, delicate balancing act to optimize efficiency.
Let's jump into Section 3, the material removal rate.
So, we know the time and the path, right? But how much raw metal is actually being carved into scrap? Well, the answer is the material removal rate, or MRR. MRR equals cutting speed, V, multiplied by feed, F, multiplied by depth of cut, D. This equation basically takes the speed of the cut, the stride of the tool, and the depth of the bite, and mashes them together to give us the actual volume of material being removed per unit of time. It's really the ultimate measure of how aggressively your machine is working on the floor.
That brings us to Section 4, solving numerical problem 1.
Let's look at our first numerical problem. Say we're given a cutting speed V of 2500, a feed F of 0.3, and a depth of cut D of 2.0. We need to find the material removal rate. And check out how seamlessly these raw variables plug straight into our MRR equation.
Let's walk through the logic deliberately here. Step 1, we identified our 3 key variables right from the machine settings. Step 2, we selected the correct formula, MRR equals V times F times D. And step 3, we just do the math. Multiply 2500 by 0.3 by 2.0.
And boom! That gives us our final answer, 1,500 cubic millimeters per second. I mean, really think about that volume for a second. Every single second that machine is running, it's carving away 1,500 cubic millimeters of solid material. It just perfectly highlights the absolute incredible power of modern manufacturing processes.
All right, let's wrap things up with Section 5, meeting the foreman's deadline.
Okay, picture this.
In a production turning operation, the foreman comes down and decides that a single pass must be completed on a cylindrical workpiece in exactly 5.0 minutes. The piece is 400 millimeters long and 150 millimeters in diameter. Using a feed of 0.30 millimeters per revolution and a depth of cut of 4.0 millimeters, what cutting speed must be used to meet this exact machining time requirement?
Now, this brilliantly illustrates a classic real-world trap. Just look at the variables we've extracted. Time is 5.0 minutes, length is 400, diameter is 150, feed is 0.3. But notice how the depth of cut, 4 millimeters, is just labeled as extra info. Why? Because we're solving for time and speed along the length of the part. How deep the tool is cutting doesn't actually affect the duration of that specific pass. The foreman completely threw in a distracting variable to test us.
So, to crack this, we just follow our deductive steps. First, we identify our given variables and our really strict 5-minute time limit. Second, we confidently toss out that extra depth of cut information. We don't need it. Third, we use our time formula to find the spindle speed, and from there, we calculate the required cutting speed to cover that 400 millimeter length in exactly 5 minutes.
When you isolate the right variables and run the math, you get your answer, 125.7 meters per minute. That is the exact cutting speed you need to program into the machine to satisfy the foreman, hit that 5.0-minute deadline perfectly, and ensure the whole factory stays on schedule.
So we've mastered the analog formulas that have driven manufacturing for decades. But as we move super deep into the fourth industrial revolution, Industry 4.0, factories are becoming totally dominated by automated robotics and intelligent networks. So I want to leave you with this provocative thought. As artificial intelligence takes over the factory floor, will it merely calculate these fundamental machining equations faster? Or will AI entirely rewrite the rules of cutting speed and feed rates in ways human engineers literally never imagined? Thanks for joining me on this explainer, and keep exploring.